All right, welcome back everybody. We are going to wrap up this module. It is a short one by walking through a example of a hypothesis test with a related samples t-test. Now, when we run a related samples t-test, just to recap again, so when we have a two-sample situation, two sets of scores gathered by the researcher are compared to each other. Each one stands in for its respective population. And we have a within participants design. In other words, we're measuring the same people twice under different conditions on the same DB. Again, there's such a thing as a paired samples test, which varies a little from that framework. We won't use those. Don't worry about seeing that in any examples on the exam. So within participants design. So let's see how this might work in practice. Again, our basic steps. The main thing that changes in this test is that everything gets converted and expressed in terms of these different scores, but that simply involves subtracting one score from the other for each participant. It involves essentially basically calculating the difference between those scores. So our hypotheses revolve around those scores. The comparison distribution revolves around those scores. We know the mean a different score in the population because the null hypothesis tells us that it should be 0. So that's what we're going to compare our actual different scores to. We have no idea of variability. And again, the shape will be a t-distribution. We'll talk about doing degrees of freedom in a moment. Finding the critical value, again, you might need to use the table for a practice example, but in anything graded, I would be giving it to you. The t-statistic, again, looks a little funky, but it's just, again, the average difference score in the sample divided by the standard error of those different scores. Still, it's just a deviation score on top, standard error at the bottom. Then we decide whether or not to reject the null hypothesis. Again, compare your test statistic to your critical score. If it's beyond that critical score, you will reject the null. If it's not, fail to reject. So here's our premise. So let's say some researchers are interested in testing the effects of something called relative deprivation. So if you haven't heard of relative deprivation, it's kind of an interesting idea. Imagine that, say, you get a summer job just like mowing somebody's lawn, and it's easy work, doesn't take too long to do, and they pay you, $30 for doing it, and you're pretty happy with that. But then you talk to a friend of yours, and he says, "Oh yeah, I used to mow that same lawn, and they paid me $100 for doing that." Suddenly, that $30 doesn't seem so satisfying, right? Even though what you got didn't actually change, the context changed. It now feels like you're being relatively deprived because another person was giving something more rewarding for that exact form of work. So let's look at an example of that. I don't usually do this. This isn't directly stats related, but I think it's funny and there's not enough humor in this class. So if you are doing this last minute or whatever, you can fast forward through this, but bear in mind that you got bigger problems than watching, a minute and a half of some monkeys getting mad. So here's the premise. Here are monkeys reacting to relative deprivation, and here's our setup. Essentially, the monkeys are being given a task. They have to pass a rock through the window, and they get a treat. They get food. But here's the thing. Our first monkey is going to do that task, and he's going to get a cucumber for that. Monkeys like cucumbers just fine. But there's also a bin next to it of grapes, and monkeys really like grapes. They prefer cucumbers to grapes. So monkey one does the job. He mows the lawn or whatever, and he gets his cucumber. All right, that's fine. I'd like some more. Now he's got to wait for the second monkey. Okay, second monkey's doing the same thing. But hang on, whoa. Second monkey's getting a grape for doing the same thing. Oh, we're getting grapes now. Here's your rock. Give me my grape. Wait, I'm getting a cucumber? Hang on, he got a grape. Nope, not happening. Notice how he's now furious at the exact same reward that he was getting because he saw the other monkey get a better reward for doing the same thing. And he is very, very vocally upset about that. So, and again, he watches the second monkey get a grape. Oh, he doesn't even want to do it. It's painful. No, I don't want to do it. No, you're not going to give me the grape. All right, let's see. Maybe give me the grape. Oh, the cucumber? Nope. Absolutely not. Give me that grape. Let me out. Anyway, just a little bit of a comedic example of that idea of relative deprivation. So let's slide that back on over. Maybe we accidentally had some fun here for a minute. And let's talk about our example. So we're doing the same sort of thing here, but with children. So we have kids play with old toys, and kids don't usually care, especially young kids, about what kind of toys they play with. So they play with some old toys. We measure how aggressive they are towards the toys. Then we give them that relative deprivation. They get to watch a second group of kids play with brand new, nicer toys that the first group of kids can't have. Then we take that initial group of kids, we let them play with the old toys again, and again count their aggressive behaviors. So we've got 6 kids here. We've got measurements at time 1 before the deprivation, at time 2 after the deprivation, and we're going to see again if we can find a statistically significant difference between those two samples. So again, the first thing we do is create our hypotheses. The symbols change a little bit. The idea does not. The null hypothesis is that the average difference score is 0, which is a way of saying basically that that deprivation isn't going to change those kids' aggression scores. Their average difference score will be 0. The alternative hypothesis or research hypothesis is that it will be different from 0, that the deprivation is going to affect the kids in some way. We would expect them to get more aggressive, but it'd be worth knowing about if they got less aggressive too. Pretty straightforward. Step 2, figure out our characteristics. We know that the mean of that difference score distribution is 0 because that's always what we're predicting here, at least in this class. Don't know our variability measures, don't have a standard deviation, don't have a standard error. We know we have a t-distribution, we have 5 degrees of freedom. How did I get that? Again, I took the number of participants, which is 6, or the number of pairs of scores, and subtracted 1. Do not make the mistake where you count up the total number of scores, 12, and subtract 1 from that. Very common mistake. It will screw you up in multiple places. It will hurt you in multiple steps. The number of participants, minus 1. Anyway, 6 participants, minus 1, 5 degrees of freedom. Here's what our data set looks like, and let's look at what this looks like in practice. So we are going to be calculating the variance for this initially, and then we are going to turn that into a standard error. Before we do that, we can get some means here. We're going to need those a little later on. Here's our difference score. How did I get those? It's just x2 minus x1. So 18 minus 16 is 2, a difference score of 2. 11 minus 10 is 1, so on and so forth. And then you just add them up, divide by the number of different scores, and you get an average difference score of 1.67. So these kids, on average, had 1.67 more aggressive actions after the deprivation than before it. You can, by the way, do a little check on that by calculating the means of each group individually and then just subtracting those means, and they should be the same distance apart, and they are. We're not done yet, though. We need to figure out the variance of those different scores and turn it into a standard error. Here, just to switch things up, I am using the definitional formula for variance. So we're getting deviation scores here. How far is each individual child's difference score from the average difference score? This kid's difference score is 1/3 of a different score above the average. This kid is 2/3 of a different score below, and so on and so forth. Notice if we added all those up, give or take rounding, they would add to 0, so we won't do that. We will square them and round to 2 decimal places. They all add up to a sum of squares of 1.34. That reflects the sum of squares just for those difference scores. It's still being calculated the way we have in the past. We can change that sum of squares into a standard deviation by dividing by the degrees of freedom, which again is 5, and then taking the square root of that. That gives us 0.52 for the standard deviation. But we're not done. Sample size bigger than 1, got to change it to a standard error. We're using the same formulas, it's just that that D subscript is showing up. The standard deviation, which we just got, goes here. The number of participants, not the number of scores, goes here. We take the square root of that and divide the standard deviation. After rounding, our standard error is 0.21. So we now have our shape. We have our mean, which again is the mean difference score. We have our standard error, which again is the standard error of those different scores. And it's being used to estimate those population parameters. Here's how we could do it using the computational formula, by the way. Notice it's a little simpler. Here we don't even need an average difference score for the sample. We will later, though, so you might calculate it anyway. But we just need a sigma d, all the different scores added up. We just need to square those, nice and easy, add up those squared difference scores, and then we plug them into our computational formula. Squared difference scores added up here. Difference scores added up, then squared, divided by the number of people. We get a sum of squares of 1.33. Notice that's a tick different than the last one, but that's just because of rounding. It's going to turn out the same when we plug it into our standard deviation and standard error formula. So when you slice it, you wind up with 0.21. That's the last piece of information in this step. It's going to be the denominator of our test statistic. First, we got to get the critical values. How many degrees of freedom? We had 5. What's our alpha level? 0.05. And again, if you look this up in your t-table, or you just take my word for it, the critical values there are plus and minus 2.51, 2.571, excuse me. It's plus and minus because it's a two-tailed test, but because the t-distribution is symmetrical, it's just plus and minus the exact same number. So we've got our little comparison distribution here. It can help sometimes to sketch this out just to brush up on what we're doing here. Any score beyond these lines has a probability of lower than alpha, and if our actual test statistic winds up in that shaded area, we will reject the null, either one. If it winds up between those two lines, we will fail to reject. Let's see what we got. So Our average difference score in the sample, remember, our mean difference score was 1.67. We have a mu piece up here, but because the null is that mu is 0, we just cross it out. And with 1.67, the average difference score divided by the standard error of those difference scores, 0.21, we have a t-score of 7.95. These kids' average difference scores is almost 8 standard errors higher than the null hypothesis prediction of an average difference score of 0. Is that enough to reject the null? Hopefully you figured this out as soon as I put that number up there. That is not only beyond the line, that's a mile beyond the line. That's an incredibly unlikely result to happen if there was no effect of that relative deprivation. So we very much reject the null hypothesis. Aggression scores after the frustrating event were significantly different, specifically higher than aggression scores before the event. It looks like that relative deprivation made those kids mad the same way it did for those monkeys. To sum it up, again, definitely be familiar with when you use all 4 tests, those earlier tests, z-tests, single sample t-tests. You're not going to have to run those in your coming test, but those are going to be options on your choosing hypothesis test questions. So both of these are single sample tests. The difference is when we know those population variance parameters, the variance, the standard deviation, the standard error. T-test for related samples occurs when we have dependent scores, meaning a within participants design, and of course we don't know any population variances. The independent samples t-test is done when there is a between participants design, different people in our different conditions. That is the end of this module. There is a practice quiz that's going to be available after this, and a homework assignment as well. And I encourage you to complete those, and again, just continue progressing through the material. Make sure you're reading the textbook and doing extra practice problems there. I will see you in the next unit when we talk about situations with 3 or more samples of scores. You use a family of statistics called the ANOVA.